Now we'll start the next complicated resistance circuit, which is symmetry rules, right? There are two types of rules which can be used for solving these type of circuits, which looks like complicated, right? And these are symmetry rules, and out of symmetry rules there are two types: mirror symmetry and folding symmetry. Right now, guys, mirror symmetry, etc., is something which you can should have an idea, because it's quite similar to that which you learned during chemistry. Isomerism, etc., you would have seen same stuff, right? Just the naming is different. So once you consider the circuit solving, folding symmetry, sometimes same circuit can be solved by both the method, and some of the circuits has to be or can be solved by only mirror symmetry or your folding symmetry, right? We'll do almost 90% of the common type of circuits, right? Then the other things you can get an idea how to solve it. So let's move on with the basic idea what is mirror symmetry and folding symmetries. So symmetry rules, first one is mirror symmetry. Right, we'll take a common circuit and we will take the Weisstein's bridge itself. That is, Weisstein's bridge you can you know how to solve, but we will solve a Weisstein's bridge using the mirror symmetry method. So let's move on with the circuit. It's 2R, 2R, this is R, okay, this is 2R, no, let's take it as R, and this one is also R, and this is B terminal and this is A terminal, right? So this is a Weisstein's bridge. Why? 2R by R is 2, 2R by R is 2, both are in same ratio, so it's a balanced Weisstein's bridge. You can remove R and then you can obviously find the answer. Let's see what would be the actual answer be, so that we can cross check whether the solving is correct or not. This R goes off, so it will be 4R, and this will be 2R, when 4R parallel to 2R. So what will be R1 into R2, right? 4R into 2R divided by R1 plus R2, that is 6R, right? That is 3. So you are supposed to get 4R by 3 as answer, right? Now let's see whether by mirror symmetry you are getting the same answer or not. In mirror symmetry, you always consider, see, suppose there had been a mirror here, where between R, then this 2R is same as this 2R, this R is same as this R. That means I can say this part is image of this part, right? Or I can say LHS and RHS are mirror images, right, of each other, right? In this condition only, that is, once you keep a mirror, it appears that the same has been repeated on the left hand side. So I'm going to keep a mirror. Let's make it as a different color. So this is your mirror kept here, right? So this is where the mirror symmetry happens, mirror symmetry, right? Now let's move on to what and all additional things we have to do. We have to connect a supply across A and B, because it is across these two guys we have to combine or finding the equivalent resistance. So this is positive, this is negative, means from A part the current will be flowing, splitting. Let's make it as this one as I1 and this one as I2, right? Now I am saying that there is a mirror here, and this is image of this part is mirror image of this part. Then if I1 is going up, then its mirror image, this side will be also having I1 but in downward direction, right? Mirror, right? So this I2, when it is going out, this will appear as coming in, right? Mirror image is left becomes right, right becomes left. This much clear? Right, this is just a figure. Now see, I1 is going and from this point, and I1 is reaching this point, means this current would have moved from this direction and this direction and reached here. Similarly, I2 is going out from this point, then I2 is coming in B, means this must have moved like this. That means there is no branching has happened in R. All the current I1 from this terminal has reached B, I2 has reached here. So no current has flown through R, right? Now this is same as this one, right? So I can remove this R. Clear? Same as the solving this one. So when R is removed, 2R, 2R, 4R, RR, 2R, So you get the same answer, right? This we are finding another way of solving. This is a common question, guys. We'll move on with some of the examples. So now later on, after doing the folding symmetry, we'll do a little bit different questions. Now go on. That is folding symmetry. How folding symmetry is done. See, guys, before moving on, in mirror symmetry, current division we are doing, right? Whereas in folding symmetry, we use potential or voltage, right? Let's move on with the circuit. So this is your circuit. Let's take another Wheatstone bridge itself, but with different value. So this is R, means let's make this one also R. This is 2R, right? This is B terminal, this is A terminal, right? Now this is 2R, right? So R by R 1, 1, 2R by 2R 1. So ratio is same, so it's a balanced Wheatstone's bridge, right? Clear? So 3R and 3R will be series. So 3R by 2 is the answer you're supposed to get. We'll see whether we are getting the same answer. Now, what are we going to do? We are going to fold, right? We are going to fold in such a way that this section, folding between A and B, right? Because we are going to feel like this. Suppose always in folding symmetry, you have to take the terminal. The folding symmetry, usually the terminal has to come along, right? I'm going to fold them. Fold them means this R is same as this R. 2R overlaps over 2R. The same guys are coming, right? So it is easy to overlap like this, folding like this, right? When we fold the circuit, one part of the circuit comes over the other, right? This is a folding symmetry. This is two methods, guys. Some of the circuits can be solved by both of them, right? So let's move on. Now I'm going to give some names. Suppose this point is X. So if I fold this much section from here to here, means this point also becomes X, because folding like this, so overlaps. Suppose this point is Y, means this point also becomes Y. Suppose this point is Z, means this point also becomes Z, because I am overlapping it. So if there is something written here, when I fold, that same written part comes over here. I hope this much is clear. Now what happens? Let's move on. Between X and Y, how many resistors are there? 2 resistors, right? So I'm starting with A, guys, right? Now I'm going to start with A, right? Now A starts, then we are moving to point X, right? Then we are going to move to Y, but X and Y is having one resistance. Similarly, X and Y is having another resistance. So I can write X and Y is having how many resistance? 2 resistance, so they will be in parallel, right? Now from Y to Z, it is having one resistor 2R. Similarly, Y to Z is having another resistance 2R. So in between Y and Z, again there is 2 resistances, right? So this is 2R, 2R, right? So that much Z is over. Clear? Now after Z, then the point is B, right? This and all resistance goes off. Clear? Now what happens regarding the point Y and Y? They are same potential, right? They are same potential. If we are same potential, means V0 and Y have, we can neglect this R, because no current is going to flow when there is having same potential. So there is an equivalent circuit. Now you can solve by yourself, right? R at parallel means it will be what? Equivalent circuit will be R by 2. Then this is 2R and 2R, means the equivalent resistance will be R. And this is B, A. R by 2 and R is parallel, means R by 2 into R divided by R by 2 plus R, right? Sorry, they are in series, right? So R by 2 plus R is the answer, right? R by 2 plus R, that is 3R by 2. Yes, earlier also we tell by method of what Wheatstone's bridge also we said that the equivalent resistance is 3R by 2. You got the same answer by this method, right? Now let's move on with the proper circuit case. This one was just to give you an idea how to do a folding symmetry and how to do a mirror symmetry. We'll go for the actual questions. Clear? Right. Now we have the second circuit. we have to see whether we can use what folding symmetry or mirror symmetry. Guys, whenever you're considering folding symmetry, usually you have to consider the points from where or across where you are asked for finding the resistance. You're asked to find the equivalent resistance across A and B. Can I make a folding across AB so that it can flip? See, across AB, right? Can I fold it like this? I hope you understood. Can I fold it like this? There is nothing below AB, so I cannot go for AB, or I cannot go by folding symmetry. Here, see, you are asked what is the resistance across AB, right? So you can flap it like this, because R is same here, 2R is same here, right? So you can fold like this. But if you are asked across A and B and you do a folding symmetry, you have to flip it here. There is nothing to flip or cross over here, so I can never go by a flipping or folding symmetry. This much clear? So obviously I will go with what? Which section? I will go with the mirror section. So you would ask me, so why can't I flip it like this? But you are asked across A and B, that is, these two terminals are separated. If you flip it like this, then A and B will be same. So you can never go by a folding symmetry. I hope you understood. See, if this section, you take this section as a folding side and you ask, this side is same that like this side, so I can obviously flap it like this. No. But you are asked between these two terminals. If you flap it like this, then this terminal A and this terminal will be also A. So the entire question becomes wrong. I hope this much is clear. So I'll go by which method? I will go by mirror symmetry method. And where I will place the mirror? I'll place the mirror here. Clear? Same. Right. Now what happens? You will do by what division? You will go by current. That is, you will give positive here, negative here, current will flow here. Suppose this is I1, this is I2, right? Then here image will be, this is going out, so it will be in I1, in I2. Clear? This much clear? Right. So see guys, here I2 is coming, the entire I2 is reaching this point, so that means there is nothing division in this point. I hope it is clear. See, I2 current is leaving from this terminal. It is going, and without any disruption here, I2 has reached here. That is the meaning of this figure, right? That means there is no sense of this point. There is no splitting, means there is no point like this. So if I redraw the figure, it will be like this. A, then this R, and this R, and this goes off till B, and there is R, this is R, that's it. This splitting never happened. Yeah, I hope you understood. Now it is easy to solve the circuit, right? How would you solve? These two R resistances are in series 2R, and these two resistors are in series 2R. 2R and 2R are in parallel, so 2R by 2, so it becomes R. Then R becomes series, so 3R is in parallel with 2R. I hope you understood what I mean. So this 2R, right? So let's see. Some of you guys cannot understand when I speedily say the circuit solving. That has to come up, guys. It's high time you understand how the solving is done. 2R, and this is R, right? Then this is R, two terminals. I hope you understood. Now this 2R and this 2R in parallel, so R by N, right? So 2R divided by N is 2, so the answer is R. Then 1R, R. The below two guys can be added, so they become 2R, R. So these three becomes 3R is parallel to 2R. So what would you do? 3R into 2R by 5R. Add them. R1, R2 divided by R1 plus R2. So 6R by 5 is your equivalent resistance value. This much is clear, I believe. Right. Now we'll move on to the next section, guys. This much circuit is not tough if you understand the logic behind it. So I hope you understood why I didn't take folding symmetry here. Whenever you're considering folding symmetry, you have to listen, or section has to be understood that you always require the terminals, and about that terminal you are supposed to fold. Clear? Right, let's move on to the next one.